Conference will now be recorded.
Yeah, good morning, everyone. I hope everyone is able to hear me.
Yes, Vikram.
Yes.
Yeah. This is the session on general purpose GPU, that is graphical processing unit CUDA programming in C++. So, I will just brief that how we will go about this session. In the beginning, it is just a sort of presentation in which it will most of the part will be covered, the introduction of most of the facilities which are available in the GPU, that will be covered, right? And from the second slide onwards, we will start experimenting, and we can I will show you demonstration of the code execution and how to write the code and the code execution in the CUDA environment, right? Let me start with the first this introductory presentation. I hope everyone is able to see it in the full screen mode. Is it clearly
Yes.
visible? Right. So if anyone have has any problem, I think he or she can raise hand. Is it so? Is it like this?
It's on full screen mode, Vikram.
Pardon? It's
It's on
working.
full screen mode. The slide. Yeah. Yep.
Is it fine now?
Yes, Vikram.
Yeah, fine.
Others, if you're not able to see, just let Vikram know the same thing.
Yeah, sure. So let's start with this basic discussion, general purpose computation on the graphical processing units, right? So traditionally, these are known as the graphics card. I just want to turn on my highlighter so that you may uh, see which part I am talking about. Uh, So second point, GPUs are quite being used since quite a long time as graphical rendering co-processor. Fine, but now the NVIDIA has made this available, this facility available for the general purpose computing. I will just skip if it is more. It's very basic one. I hope all of you have some basic idea, or I should start from this basic slide.
Vikram, I think it's fair to start from the basics anyway. Be useful for everyone, even if
Okay,
some
okay.
of them may have a background, not everyone would have.
Okay, fine. Right. So GPU is typically a computer card. Basically, if it is a desktop PC, it is installed into the PCIe slot, and if it is on the laptop or notebook, it is on board, right? So market leaders in this field in GPUs are NVIDIA, Intel or AMD. So these are different. Some of the picks of some of the GPUs like GeForce GTX 480, GeForce GTX 1050 Ti, Tesla 2070, right? So NVIDIA has hundreds of GPU cards with different hardware capability. Now we will see what does this hardware capability means. So basically, what is GPU computing? This is basically it is the use of GPU together with the CPU. As of now, we do the C++ or any language programming on the PC. That we can call it as the CPU programming if you are not using the GPU, right? But so in this case, even in the GPU computing, the code is mixture of the CPU as well as GPU. So CPU will control the all the computation part, right? What happens that CPU sends the task to the GPU. GPU performs the computation on the data and sends back results to the CPU. So CPU act as the host, right? And GPU is called as the device. This is in the context of the GPU computing. So this is the one important thing we have. We are in the beginning of GPU computing. We must understand that GPU is called device and CPU is called host. Now, of course, all of you are aware that why, as you have opted for this course, that why you need GPU computing, because it we can make our code parallel. There are number of cores available on the GPU. In the CPU, there are only few cores. Maybe in the quad core, there are 4 cores. In the dual core, in the 2 cores. And in the GPU, there are thousands of the cores. So we can make our code parallel, right? So as we discussed, GPU does, how does GPU enhances the efficiency of our code? It does it by parallel processing. So now GPU consists of basically thousands of smaller, more efficient cores designed for parallel performance. And what about CPU? CPU consists of few cores optimized for serial processing. For example, as we discussed, Intel Pentium dual core has 2 cores, quad core it has 4 cores, octa core 8 cores, and most consumer CPUs have cores between 2 to 12, right? And workstation CPUs may feature as many as 48 cores, but still these are very few. So if we in the GPU computing, the serial portion of the code will run on the CPU while the parallel portion will run on the GPU. It means we are in the GPU computing, we divide the code into 2 parts. One part which we can which we can be converted into the parallel processing, and another part is the serial part that will execute still on the CPU. Now we see brief of CPU versus GPU architecture, right? So regarding its hardware part, GPU devotes more transistors for computation, right? So GPU contains much larger number of dedicated ALUs than the CPUs. So it has large number of arithmetic logical units as compared to CPUs. So each processing unit on the GPU contains local memory. It has its own memory. So it improvises the data manipulation and reduces the fetch time. So if we see the architecture of the CPU, it has a control unit. There are only 4 ALUs. There is a cache and there is the dynamic RAM. But if we see the in the right side, if we see this basic architecture of GPU, it has a number of processing unit, and each of the processing unit has its own ALU. And there is the common dynamic RAM, which is called as the global memory also. So if we talk about a sequential program, it will only run on one of the cores, which will not become any faster. So with each new generation of the processors, software will continue to enjoy the performance improvement with the parallel programs. So parallel program is a very good option for enhancing the speed of our processing of the programs. In this multiple threads of execution cooperate to achieve the functionality faster. They are so in this basically this is a multi-threaded programming. In GPUs we can launch the as many threads, 100 or thousands or billions of threads which execute in parallel. So that is the where the power lies in this GPU computing. Now if we talk about CPU only, the processor performance can be measured by the rate at which it executes the instructions. That is the clock frequency. So it is measured in the basically million instructions per second, uh, which we can say that frequency multiplied by average instructions per cycle. So if we want to enhance the CPU performance, either we will have to increase the clock frequency or by increasing the number of instructions that can be executed in one cycle. So there is always limit in this in enhancing the hardware capability of CPU because of the complexity and the power consumption. So we can see just a rough idea of comparison of CPU versus GPU performance in how many giga flops. So these are the different GPU cards. And so there is a lot of gap in performance of GPU. So this is the graph of NVIDIA GPU single precision, double precision GPUs, Intel CPU double precision, and Intel CPU single precision. So just to get an idea that how much is the performance difference between GPU and CPU. Now GPU we can call it as a numeric computing engine. It will not perform well on some tasks as CPU. Some tasks they are good to perform on CPU if they are very complex, and most application will use both CPUs and GPUs. So the solution is to use the combination of CPU and GPUs. So here comes the CUDA, that is the Compute Unified Device Architecture. This is basically the solution provided by the NVIDIA for parallel computing to access the parallel computing power of their graphical processing units. So, and this is the NVIDIA's parallel computing architecture aimed at increasing computing performance by harnessing the power of the GPU. So, it constitutes the programming model. It is basically based upon C, C++. So, we can see on the website of NVIDIA there are hundreds of GPU cards available. For example, some of the example specifications of some of the GPUs like GTX 480, it has peak double precision floating point performance. This is 650 gigaflops, and for Tesla it is the 515 gigaflops, right? Then peak single precision performance for GTX 480 1300 gigaflops, and for Tesla, right? Now this is CUDA cores. This is the feature which is more useful for the programmer to see that how many parallel threads we can launch. More the number of the CUDA, more the number of the cores, more the number of the parallel threads we can launch. Now, what is the frequency of the CUDA cores of the 1.40 gigahertz for GTX 480, and for Tesla it is 1.15 gigahertz. Similarly, memory size of order of 1536 megabytes, and for Tesla 20706 gigabytes. So this is just an idea of the specifications of GPU, some of the GPUs. This is the another GPU GeForce GTX 1050 CUDA cores. It has 640 CUDA cores. Graphics clock is the 1354 megahertz. Processor clock is the 1455 megahertz. So these are then memory specs. There are 2 gigabytes of memory. Memory interface width is 128 bit. Just a second. So features available in this are, it supports different features. As of now, important for us is the CUDA. There are other features which are supported technologies like 3D vision, SciX, NVIDIA G-Sync, Ansel, and ShadowWorks. So thermal and power specs are also there. Maximum GPU temperature 97 and max in degree Celsius, and maximum graphics card power is 75 watts. So we can see the specifications of different cards on the on NVIDIA's website. Basically, we must know what the capabilities, if we are having GPU, and what are its capabilities, so that we can check from its specifications which are available on the NVIDIA's website. So these are the some applications. Just it can be used. GPUs are being used in the computational structural mechanics, bioinformatics, electromagnetics, computational finance, in the computational fluid mechanics. These are the scientific fields: data mining, imaging and computer vision, medical imaging. Then in molecular dynamics, numerical analytics, weather forecasting, etc. In the ocean modeling and in the space sciences. Now, well, we have just heard a lot about its basics. So we should why should we should learn it, or we should use it, because we want our applications to run faster, or if we want our if we have doing any simulations, they can converge faster, or we can apply the concepts of parallel processing to our code. So there are so many reasons to dig into the GPU computing. So now we come to the main part, that steps. We have to start with the GPU computing. So what are the steps one must follow to start with the GPU computing? Now all of us are aware now that why we are going for GPU computing, because it provides a number of cores, and we can launch the when we can do the multi-threaded programming. We can make our program parallel, and we can enhance its efficiency, because it is very much important if we are working into the heavy computational task like machine learning or image processing, right? So what are the steps for learning of GPU computing? First of all, we should go through the study architecture of the CUDA, that is the compute unified device architecture. We should learn about tools to be used for its development. We have to select the which platform of development we want to use. For example, which OS we have to work on, Linux or on the Windows environment, or which language we have to work into, C++, or Python, or Fortran. Any because NVIDIA supports CUDA supports a multiple languages for its development. So then afterwards we should learn the CUDA programming basics. So that is the steps to be followed for learning of GPU computing. Now we will go through the first step, that is the, as we discussed here, study of architecture of the CUDA. So that is the first step. We will go through the CUDA architecture, right? So basically CUDA is NVIDIA solution to access the GPU. I hope everyone is able to see the slides.
Yes, we can, Vikram.
Fine. Okay. So CUDA is basically NVIDIA solution to access the GPU, right? It can be seen as an extension of the, so C++ can be the mother language of the CUDA, right? It was the first language support which was provided by the NVIDIA. Later on, they also provided then Fortran, and then now Python, and there different language support is now available for the CUDA programming, right? So we can see that this is the CUDA software stack. We have the device, right? That is the GPU device. Over it is the CUDA driver, right? That is basically provided by its GPU driver, graphics card driver, which we can install on our PC, right? So then there is the CUDA runtime environment. Then there are CUDA libraries, and so these all are installed on the host, right? And host and device, they are connected through PCIe slot, and our applications run basically on top of these this CUDA in host environment, right? Our program will execute in the host environment, and we can send the commands to the GPU for parallel computing. Now more about the CUDA architecture. As we discussed, there are basically two parts: host part, that is the CPU part, which works on the principle of single program, single data, right? And device or the GPU part which runs on the principle of single program, multiple data, right? So we can see that this is the host first part, and then second part is the device. Basically the program, the parallel, the function, basically this this is the new term. Kernel is basically the function which has to be executed on the device. The function, the parallel function, that is called as the kernel. For example, host can launch the multiple kernel. There is a kernel 1 and kernel 2. So in terms of C, C++ or any language now, as of now, we can see the kernel as the functions which exhibit the parallel computation, right? So now on the device, how the kernel is executed on the device? Basically, it is executed in the multi-threaded environment. A kernel means it is launching the multiple threads, right? So basically, multiple threads are basically are grouped into different, you can say, categories. They are grouped into grid. At the higher level, the topmost category or the biggest category is the grid, and a grid contains blocks and blocks contains threads. So we can see that. So there are three kind of grouping: grid, block, and thread. And we can see that grid is the superset or the superclass, and inside the grid there are blocks, and block is made up of threads. So grid is made up of blocks and block is made up of threads. So, and there's indexing. We can address the threads inside the block with some index, and we can access the blocks inside the grid with the index. So all three have some indexing facility which is provided by the CUDA, so that we can manipulate a particular thread. Now we coming to the CUDA architecture. More about CUDA architecture, as we discussed about the grid is the topmost category or the superset. So basically it is a group of threads all running the same kernel, means same function. All the threads in the group, in this grid, they are running the same function, right? So this is its, you can say, simple definition. A GPU can run multiple threads, that multiple kernels at once. So because all the kernels are executed in parallel, these are not sequential. So multiple grids means multiple parallel functions. So they can be executed in simultaneously. Now next category is of the blocks. So we can see that in a block, grids are composed of blocks, and each block is a logical unit containing a number of coordinating threads. So that is the important point, coordinating, that threads are can coordinate with each other within a block, and they have some amount of the shared memory, right? So the threads within the block, they coordinate with each other through this shared memory. So in this diagram we can see that at the topmost category, blue one, that is the grid. Inside grid there are two blocks, the block 0 0 and block 1 0. So these are its x index and that is its y index. So you can see that dimension, this is a multi-dimensional addressing of the blocks, right? X index and y index. So each of the block has a shared memory. You can just change the color for the time being. So each of the block has the shared memory. It has registers. We can see the hardware functionality which is available. Registers are available in each block. Then there are multiple threads which have thread indexing, like thread 0 0, thread 1 0. We will see in detail how the indexing is done. Each of the thread has its own local memory. We can see that each of the thread has its own local memory, right? Then there are three kind of memories which are shown over here. One is this global memory, right? This is the global memory. Then there is the constant data which can be fed into the constant memory. So global memory is also called as the dynamic RAM, and it is read write memory. We can write into this and we can read it from this global memory. While constant memory and this texture memory, these are the read only memories. uh, this is the constant memory, that is also read only memory, and texture memory, that is also read only memory. So now we come to the CUDA processing, which is based upon single instruction, multiple data. How the processing is done? We are seeing just the basics of the CUDA architecture. We will go into its detail. So this is single machine instruction, multiple data. This is the basic. This is a single instruction, multiple data. So means multiple data means we can work on to the huge amount, large size arrays. There can be million of elements or billion of elements in our array. It means that is the multiple data, and we are processing single instruction on all the elements of our array. So it controls the simultaneous execution of a large number of processing elements. We can process a number of elements in parallel. Each processing element has associated data memory. Each instruction executed on different set of data by different thread processor. So in the diagram we can see that, for example, we are doing multiplication, element by element multiplication. So for example, this is the first element, then second element. So this is just example of single. I'm getting this sound. I think is there any problem? Some sound is coming multiple times. Hello. Hello.
Yeah, hi. I think it is just people joining or exiting the call.
Okay, okay. I thought there's some problem because actually in online mode, I am just focusing on this slide. I am not able to see what is going behind. So that's why I was asking. Okay, fine.
Yeah, I think it is just people joining, exiting the call. Maybe we can turn off that option.
Okay,
There's probably a way to turn it off.
fine, fine. No issue. Fine. So we will going through this slide. That is the CUDA. Basically, the principle is single instruction and multiple data. Multiple data we can means that we can work on the big amount of data or large arrays, which can be single dimensional array, it can be two dimensional array, three dimensional array, or multi-dimensional arrays we can work. Now we come to the GPU threads, which is the main, we can say, building blocks of our computation, GPU computing. Because GPU computing is based upon launching of the multiple threads and how they threads interact with each other, how these thread can read or write to different type of memories. These are the main issues we should address in while writing our GPU code. So we must understand about the GPU threads. So GPU threads are basically extremely these are extremely lightweight. These are very lightweight processing units, and they have very little creation overhead. So GPU needs thousands of threads for full efficiency. So we can launch the thousands or millions of threads for its full efficiency. But if we talk about multi-core CPUs, they need only very few threads. Now, again, we come back to the thread batching or grouping in grids and blocks, right? So, as we have discussed that our kernel is basically our parallel function, which has to be executed on the device that is on the GPU. A kernel is executed as a grid of thread blocks. So, all the threads share data memory space, right? So a thread block is so now if we come to the block, It's a batch or group of threads that can cooperate with each other by how they cooperate with each other. They cooperate by synchronizing their execution for hazard-free shared memory access. So, say they synchronize with each other through shared memory, and there are of course some other hardware facility are also available for their cooperation. Then efficiently they can sharing data through the low latency shared memory, right? So two threads from different blocks cannot cooperate with each other. If they are only the threads which are inside a particular block, they can cooperate with each other. But if the threads are from different blocks, they cannot interact or cooperate with each other, right? So in this diagram also we can see that there are multiple kernels, and each kernel is having its own grid, and it is having multiple blocks within each grid. Now we're coming to let's come to the indexing, because that is very important. Because if we are processing a number of elements, for example, we have to process an array of 1 million elements. So there are 1 million elements. It means 1 million indices. We have to access the each element by a particular thread. So thread index means element index. By the thread index, we will be accessing that particular element of an array. So threads and blocks have IDs. Each thread can generate its own index for data, right? So blocks can be 1D or 2D. So indexing of blocks is 1D or 2D, right? But indexing of threads, it can be 1D, 2D or 3D. Right, it means there may be two indices to access, that is x index and y index for the block, and for the thread there are three indices: x index, y index and z index, right? Now it simplifies the memory addressing when processing multi-dimensional data. So when we are processing the multi-dimensional data, each element can be accessed by a particular thread, that is its unique index. Now we come more about this different memory space which is available. CUDA device memory space. Each thread can read write per thread. It can read write its registers. There are registers available. It can read write its local memory. It can read write its per block shared memory. It can also read write per grid global memory. It can read per grid constant memory and texture memory. So we can see that this a constant memory, texture memory and global memory, it is separate for every grid. Every grid has its own constant memory, it has its own texture memory, and it has its own uh, global memory. And host, if we talk about the host, so this is the host part over here, and this is the device part, right? Host can, how do host communicate with the device? Host communicate with the device through global memory, through constant memory and through the texture memory. Host can read or write to the global memory, host can read and write to the constant memory, and host can read and write to the texture memory.
Vikram, sorry to
Yeah.
interrupt. One question. What is the difference between global memory, constant memory, and texture memory in terms of
Yeah,
the structure or the functionality?
we can just I can give you brief idea at this stage. See, global memory is just like the RAM. It's you can say every process, all the blocks need this. Each block has its shared memory, right? And multiple blocks they share. They can read and write to the global memory. So global memory is the general purpose read RAM, right? If constant memory is the read only memory, right? they can all the blocks can just read from this constant memory. Okay. And if we talk about texture memory is a type of memory which is used mostly for the we can say graphical processing. Like it has some hardware functionality to for the faster access of nearby elements. If we are accessing one element, so it is faster access of the nearby element. So it means some texture from the name it suggests. So it is used to for generating the texture. So textures are also, we can say, that repetitive in pattern. In the same way, in the nearby of that particular location, it will give better efficiency. We access the elements near that particular element, in the neighborhood of that element. So that is the additional functionality of the texture memory, right? At this stage, just we need to we will go through just basic idea of these different memories, right? And in a few further slides we will be
So for image processing applications,
right.
which one do we typically use? Can the user choose one over the other?
Yeah, we have to see basically as per the efficiency, which memory or by which accessing technique or which addressing techniques give us the better efficiency. So in the next few slides, we will be focusing on the global memory also only, and then later on will go through these two memories, constant memory and texture memory, right? So most of our task will be handled through global memory only, right? Uh, is it okay? Hello, can
Yes,
I?
please carry on.
Yeah, fine. So now the different memory units. If we talk about the efficiency part, if we talk about registers, they are fastest, right? They are only accessible by threads, and they are alive till the lifetime of a particular thread, right? Now, if we talk about the shared memory, it can be as fast as a register if there are no bank conflicts or reading from the same address, right? It can be accessible by any thread within a block where it is created, and shared memory data is available till the lifetime of a block. Now we come to the global memory. So global memory basically it is 150 times slower than the registered registers or the shared memory. It is accessible from either host or device. Uh, and it is the variables declared in the global memory are alive till the lifetime of an application. Then if we talk about the local memory, it resides in the global memory. It can be 150 times slower than the registers and shared memory. It is accessible only by a thread and for the lifetime of a thread. So this is particular to a thread only, local memory. Now overall computing architecture, just we can see that there is the host, then there is a assembler which will convert our code into this executable on the device, then the thread execution manager, then there are different thread processors. uh, this is just we will go through its overview, and there is all the threads can access from the global memory. So there are different thread processors which can access the parallel data cache. As if I'm skipping these two slides just with basic intro. Now coming to the another concept, that is the CUDA warp. Basically, warp is another important concept in the thread programming or thread management. So basically, CUDA warp means the group of threads, and warp contains 32 threads. So CUDA utilize single instruction, multiple thread. Warps are basically groups of 32 threads. Each warp receives a single instruction and broadcasts it to all of its threads. So basically, these warp is the concept in which these threads are executed in group of 32, which are called as warp. So CUDA provides zero overhead warp and thread scheduling. Also, the overhead of thread creation is of the order of 1 clock. Because a warp receives a single instruction, it will diverge and converge as each thread branches independently. Now we coming to the hardware. Now we come to the what are the technical requirements if we want to make our PC ready for the GPU computing, right? We have installed the GPU device on our machine. So first of all, we need to must have hardware part. We must have a GPU card which is CUDA capable. Not all the cards are CUDA capable. We have to see on the NVIDIA's website that which of whether our card is have CUDA capability or not, right? So if it has a, we have to first of all install the device driver that is available on the NVIDIA's website. So first step for making our machine ready is install GPU, or we must our laptop or desktop must have GPU. Then we must install its device driver, right? Even if we don't have GPU on our device, we can have it on cloud. We can have this facility through cloud from AWS or Azure or IBM software layer or any other cloud service provider. We can have it through cloud, this service on through cloud also. Then we can get the GPU device driver from NVIDIA's website, right? So this device driver is first step. It is important. Only then our programs can communicate with the hardware, or we can do the CUDA programming. Now we can check the device driver info through our device manager, right? Uh, we can go through NVIDIA control panel if we have installed the driver. Then our desktop on the right, when we right click on our desktop, we will see the NVIDIA control panel functionality available, and then we can go to the help and system information to see the details of our card, of our driver, right? Also we can check whether GPU our driver installed properly through command prompt. We can type dx diag and then go to the renderer tab, and it will show the GPU card installed on our machine. So in this slide, I think if anything, if any query regarding this, do I need to show it in practically how to check, go through, check the device driver info through device manager?
Yes, I think it might be a good idea for everyone.
Okay, fine, right. Right. For example, I have installed the GPU. I have GPU on my machine, that is the GeForce GT740M. Now I have installed the device driver from NVIDIA website, right? Now after installation, I can check its details by checking, first of all, is by going through device manager, by going to the properties of my PC, and then I hope everyone is able to see device manager, right? It's the
Yes.
this option is available over here, device manager. And in the display adapters, we can see that there are two cards. One is Intel HD Graphics 4000, and another is my graphics card, that is NVIDIA GeForce GT740M, right? So this is here we can see that whether our driver was installed properly or not, right? We can go to its properties and see that our device is working properly, and we can see its driver details. This is just for the information that our driver has been installed properly, right? So that is one thing, is the one way through the device manager, right? And second way, on the desktop, I right click and I will go to the NVIDIA control panel. Means NVIDIA control panel, this facility or this you can say option will be available when our driver has been properly installed. I can go to this NVIDIA control panel. It takes some time because it's a bit heavy application. So we can see different facilities available for our graphics card or different settings. I told you in the slide that we should go into the help and then system information. So it will display all the details about our driver, right? So this is the name of the card. I hope everyone is able to see. Is it readable? GeForce GT740M?
Yes.
Yeah. So this is the driver version, that is 425.31, driver type standard. Then these are other CUDA cores. You can see how many CUDA cores are available in this machine. In the 740, number of CUDA cores are 384. What is the graphics clock? We can see 980 megahertz. Memory data rate is the 1.80 gigabits per second. Memory interface is the 64-bit. Memory bandwidth is the 14.4 gigabits per second. Gigabytes per second. So so we can see these are the different hardware features we can see of our device installed, right? So third way to check the detail about our driver is we go to the command prompt, right? We can go through either by typing here, and we can go open the command prompt as administrator, run as administrator, the command prompt. Then as I told you, dxdiag, we have to type dxdiag and then press enter. So it will open up the dialog DirectX diagnostic tool, and in this we go to the renderer option, renderer tab, right? So we can see that here it is mentioning the name of our NVIDIA GeForce GT740M card, manufacturer NVIDIA, right? I hope it is readable to all of you. Chip type GeForce GT740M, right? Then the device type renderer only display device. So these are the different display memory, VRAM. These are the different hardware features. Shared memory, you can say, 4036 MB, right? Around 4 GB. So these are the different hardware facilities which are available on our machine. I think this is an option of save all information. We can save it on this over in any file in text format. This whole information will be saved into the text format. I can exit this. So this is the text file which was saved on the desktop, dxdiag. So all the information related to our system is saved over here. It also contains the information related to our graphics card, I suppose. Yeah, this is over here. Over here, card name GeForce GT740M, manufacturer NVIDIA, chip type. So different hardware specifications we can see on our this text file, which was generated by dxdiag. Some sound is coming, I must say. It's okay now. So let's continue from the next slide. Once we have installed the GPU driver, then our machine.
Vikram,
Yeah,
I
yeah, yeah.
have a
There is.
question.
Yeah. Yes.
Uh, Vikram, so just a query. So, related to the previous slide, you did talk about grid being a superset of a block and then that being a superset of threads.
Yeah.
How do they relate to the number of cores?
Yeah. Basically, these cores are divided into these multiple processing elements, right? And there is basically when we see, I will go through in the next slide. When we see its hardware details, in its hardware specification, it is mentioned that how many maximum number of threads we can launch, right? As I told you, how many maximum number of threads can there be in one block, and how many there can be maximum number of blocks into one grid, right? So that put the limits on the threads that is related in hardware to the number of cores basically. So the cores are responsible for the this launching of thread basically in parallel, because this I just we can we can just I think roughly have an idea that these cores are divided into the multiple processing elements of the GPU, right? And each processing elements has capability to launch some number of threads. So in this way, the cores is basically hardware feature, and threads is the software concept, right? So cores are responsible to launch it in the threads, right? Because each thread requires some hardware resources, right? And each core has some capability in terms of memory, in terms of its you can say different type of memories available, and each thread also needs some resources. So threads are provided by CUDA architecture, and cores is some hardware feature, right? So this translation from threads to the cores is done through CUDA driver, right?
Okay.
Fine. Okay.
Okay.
Can we say a thread is assigned one ALU, like it is
Pardon?
completely owning one ALU in? Okay, can we say like one thread is completely owning one ALU in your GPU unit?
You mean to say we want to launch only one thread?
No. I'm saying when a thread is launched, it
Yeah.
is owning one of the ALU unit, like that. That ALU unit is not shared across thread. Like it is one thread is assigned one ALU, or say the core.
Okay.
Can we say this by when we create a thread?
Okay. No, one thread. Basically, there are multi processing units in this our GPU. So each of processing unit has its own ALU, and each processing unit can support some number of threads. So multiple threads.
Okay.
Yeah, maybe each thread is having its own local memory, but ALU may be shared by some threads, or within a share within a particular block. All the threads may be sharing a particular ALU.
So maybe in a high level to map to the CPU side, right? If we have 4 CPUs and we have 16 software threads,
Right.
so we can map say 4 software thread to one CPU and so on, right? Like in that concept, is it similar? Like having the CUDA cores that you mentioned, like 500 CUDA cores, right, in one of the graphics card.
Yeah.
So those are the processing elements, the actual hardware resource.
Yeah.
But the threads is more of a software concept, which gets mapped to each of the, those each one of those CUDA core can execute multiple threads in time division, right? Is that concept?
Yeah. Each CUDA core can execute multiple threads. That's right. That is right.
Yeah.
Because cores are limited. If we say there are 384 cores, but we can launch a large number of threads. It can be 1 lakh threads or 1 million threads we can launch, or more than that.
I see. So I think the thing that we are trying to understand probably is how does it work in terms of sharing that process? Do you plan to cover that in more detail? How GPU manages that?
Yeah. I will be going through that. Fine. That
Okay.
yeah. Now, okay. Now
And
coming to the
we
next.
had,
Pardon.
I had one more question regarding the memory. So the global memory, is it the memory that that is in the driver that you show, the total memory? Uh, which memory corresponds to global? What is the size?
Uh,
How do we map? Yeah.
yeah. I that I will show you. Basically, when I will show you one slide or one file. Actually, we will also go through in the next few experiments how to retrieve the information of our hardware through a program, right?
I see.
And
Okay.
there is some
Okay.
facility also available through which we can query the device and see its hardware resources and software resources, right? So
Okay.
fine. So after the GPU device driver, next is that we next facility we must have on our PC is the C++ compiler, right? Our native C++ compiler for the C, because our code is made up of two parts, serial part and the parallel part, right? So the serial part of the code will be compiled by the host compiler over C++ host compiler, and for parallel part of compilation of our parallel part of our code, or we need another compiler which is provided by the NVIDIA that we will discuss in the next slide. So we need to have some C++ compiler for our CPU code. uh, Fine, we should have an appropriate C++ compiler for our CPU code, right? We should select appropriate compiler as per our OS platform. Fine. For example, our machine can be x64 or x32 platform. Accordingly, we should select the compiler. It's a 64-bit version of compiler or the 32-bit version of compiler, right? So even if we are using any IDE, we may be using the Visual Studio or any other IDE. In this, we must select a platform to x64 in the configuration. If it is our x64 configuration properties for your project in Microsoft Visual Studio, right? But if you are using even any other compiler, for example, you are using any other tool. For example, we are using Edit Plus. We will be using Edit Plus, a simple tool in which we can write the program and configure it for compilation and execution. We should make sure to configure in the path x64 compiler version, right? So that is one thing, configuration of particular compiler, right? Then we come to the next requirement is the CUDA toolkit, right? Once we have installed the we have installed the particular driver compiler, then we must go to the installation of CUDA toolkit, right? That is the important part, right? So CUDA toolkit, it's a standard, basically a development kit. For the development of a CUDA program, we need to install the CUDA toolkit, right? So what is inside this CUDA toolkit? It includes the CUDA C++ compiler. As I told you, this compiler is required for compilation of our parallel code, right? So name of this compiler is NVCC, the NVIDIA C compiler, right? It will required, as in the previous slide we discussed, it will required pre-installed C++ compiler, right? It should be included in the path or configured in the respective ID, right? uh, So we can get the NVIDIA toolkit from this is the link from where we can download the NVIDIA CUDA toolkit, right? Now we can check the once we install the CUDA toolkit, we can check our compiler NVCC, right?